The paper I chose was Comprehensible Rendering of 3D Shapes by Takafumi Saito and Tokiichiro Takahashi. The purpose of this paper was to create 3D images with enhanced visual comprehensibility, which is essentially edge detection. It uses 2D image processing algorithms instead of line tracking, which makes it useful for interactive applications. And it uses something called G buffers or gay buffers, which are a type of buffer that stores things such as the screen and world coordinates, the normals, and the depth. Storing all of this information might not seem like a new idea, but this paper was published in 1990, so it was kind of a novel approach to keep all of these things around, such as always storing the world position and the normals and everything. So here's an example of a gay buffer in action. You can see at the top there's three x, y, and z values of the normal, and then underneath that there's the depth values, and OU and OV at the bottom are patch coordinates. So you can see at the top they combined all three normals to create a shaded image. The second image in the middle is just the edge detection, which was done with the edges, and the bottom ones in the middle are some curved hatching, which you can do if you implement contour lines. And these can all be implemented in various ways to create interesting variations of cross-hatched and contoured drawings. These are some results of a few passes they did on an image of a nut. And you can see at the top there's just the depth image that they created from the depth information stored in the buffer. And under that are first and second order differential equations that they use to detect the edges. And below that is the profile image and the internal image, edge image, which are just different, different ways of calculating the edge. So to find the edges, you take the depth information for the image and you store it in the buffer, and then you apply first and second order differential operations to it. So these are the equations that they suggested to use. For the first order, this equation of G equals all of this stuff. And then the second order is the one below it, which is L. And after you acquire all of these, then you can apply corrections to it. But I'll explain the process next. Oh, sorry. Also, all of these letters are just the neighboring pixels, where X is the one that you're operating on, and A through H are the ones surrounding it. So the way you implement this process is you first run a vertex shader over the whole image, which just gathers the depth and normals for each pixel. You store that in a special buffer, which I explained a second ago, and then you feed this information into the pixel shaders. So first you run the first order equation, which is the G equation from the last slide, and due to the way shaders work, passing information to each other, since you want to run it on every pixel and then run the second order on every pixel, you need to store the first order into one buffer, and then run the second order pixel shader, which takes the information from the first order and runs it through its filter. And then finally, you can draw it to the screen after you have all of that information. So limitations of this paper, I think it probably assumes some prior knowledge, because I found myself reading it over and over, trying to find little tiny hints of what they really meant for you to do in a certain situation. This picture here, I don't believe that this is actually a truthful result, or maybe they mislabeled it, because when I run second order differential equations using the suggested equations that they had in the paper, it didn't look anything like this. So I think this is probably a combination of first order and maybe the profile edge image, or a few things which aren't the second order differential anyway. Their edge detection algorithms suggest that you divide by 8 for the first order and divide by 3 for the second order. And while this does detect edges, I found it very faint, and I had to mess around with those values in order to make it stand out more and be easier to see where the actual edges were. And finally, my computer doesn't support anything above Pixel Shader version 2.0, so I could not implement correction filters because my shaders wouldn't accept conditional branching. So here is my demo. I used a Lego block that I found on turbosquid.com. because I couldn't find a nut or anything like it. But anyway, here's the depth map, which is contained in the gay buffer, and here's the normal x. It's kind of hard to see in this, but you can tell that there are differences in the values, and I'm just returning the normal x value that it gave me. Here's the normal y, same idea. Very faint differences, but they are there. The normal z. And here's the first order differential equation applied to the edges. So you can see that the edges which are on the inside, such as the edges of the hole, are much fainter, and the ones on the top. And the second order is just sort of more intense, I guess, and you can more easily see the inner edges. You can see that there's a second ring in the hole of this Lego. Yep. In future, this could be extended to include contour lines or cross-hatching, or be applied over the default image, but this will take more time. So, any questions? Just kidding, haha. Also, another thing I should mention is one of the reasons that my second order differential equation looks different from theirs is that they're somehow returning negative and positive values for the depth, or I guess the depth of where the edges are, and I was only able to return positive values, so it's only displaying in white rather than white and black, but it's still detecting the edges. So.